Hello. Yeah, good morning, students. So, in the other day, we stopped at the magnetism and matter, that is chapter 8, and we stopped with one concept, that is relation between magnetization and magnetic intensity. So, in this, we are obtaining the relation between magnetization and magnetic intensity. The magnetization that already we discussed, that is converting a non-magnetic material into a magnetic material, that is magnetization. And magnetic intensity means at what extent the magnetic field can magnetize, that is magnetic intensity. See here, this relation explains about for what magnetic field, how much magnetization can take place. I am repeating, at what magnetization or magnetic field, at what extent the magnetization takes place. So here we consider solenoid for this, and solenoid is a device that produces magnetic field. For that magnetic field, we obtain expression V0 is equal to mu naught Ni. Here mu naught is the permeability, N is the number of lines per means number of turns per unit length, and I is the amount of current which is flowing through. So this is what is the magnetic field due to solenoid. And now to magnetize, we need one piece of iron or any ferromagnetic material is kept inside this solenoid. Then it gets magnetized, means that is also behaves like a magnet. So due to this material, that is piece of iron or any ferromagnetic material, it generates some magnetic field that is indicated with a B suffix M, that is magnetic field due to material, and BO is magnetic field due to the solenoid, and together the net magnetic field is generated. This is B is equal to BO plus BM. This is net magnetic field produced in the solenoid. Now, Bm depends on the magnetization of the material. Means, what is that? Magnetic field generated due to the material that depends on material. So, what kind of material we selected? So, that depends. So, magnetization of this material depends on what type of material we selected. So, that material is nothing but permeability. So permeability, based on the permeability, this magnetization takes place. So here is the relation. Magnetization or magnetic field due to the magnetic field, this is material depends on the magnetization. This is the relation. Bm is proportional to capital M. So capital M is the magnetization, and Bm is what is the magnetic field due to the material. So to avoid this proportionality, we are keeping one constant here, mu naught. So this is mu naught that we know. Okay. So here all the definitions already we discussed. All the definitions we discussed in the previous discussion, that magnetic intensity, magnetic susceptibility, relative permeability, all these things that we discussed already. Okay, so here we obtain the relation Bm is equal to mu naught M. So we have a relation from magnetic intensity. If you see the previous discussion, magnetic intensity already we discussed, that is H. So we obtain the relation for that also. That is B is equal to mu naught H plus M. Okay, so H is the magnetic intensity. So here this expression, see next equation number 1 is given here, B is equal to mu naught H plus chi H. So this chi relation already we discussed in magnetic susceptibility concept. See, we just to revise the previous discussion. then all the definitions we have discussed over there and obtained some equations also, and those equations I'm substituting here. So here chi is the susceptibility. So in the place of whether this M can be written as chi h. This is an equation. This is an equation. So M is equal to chi h. Okay. So that equation, that value is substituted here in this equation number 1. Now from equation number 1 means we can rewrite this. B is equal to mu naught. H is taken common. Then 1 plus chi. So this already we discussed in the relative permeability concept that mu or mu suffix r is equal to 1 plus chi. So this 1 plus chi in the place of C, this bracketed term, just we replace in this next equation that B is equal to mu naught, mu r and h. So this is the equation. And again, if you go through relative permeability discussion concept, there the product of permeability of free space and the product, this one relative permeability gives the permeability of the medium, that is mu. Okay, so we can rewrite mu naught into mu r as mu. So finally we obtain the equation B is equal to mu h. So this is the relation between magnetization and magnetic intensity. Magnetization and magnetic intensity. So finally, what is the relation between them? Is a directly proportional. B is equal to mu h. Here mu is constant. So B and h are directly proportional. That is, if magnetic field is increased, then magnetization also increases. That's what is the relation. If magnetic field increases, magnetization also increases. So this is the relation between this magnetization and magnetic intensity. So now we will move on to the next concept, that very important, Earth as a magnet. Earth as a magnet. So here, very common discussions to be made here, very general. Here, the freely suspended magnetic needle, that is compass. You might have seen the compass. On that, see, compass is nothing but a finely shaped magnet. A finely shaped magnet, that is magnetic needle. We call it as a compass. It is always shows aligns to north and south directions. It is because of the external magnetic field applied by the Earth. See here, what is the title? Earth as a magnet. Now we are going to prove that Earth behaves as a magnet. So how we can say that Earth behaves as a magnet? So here is a small tool that we are using, that magnetic needle, that is magnetic compass we are using. So here compass always shows, the needle always shows north and south directions. Imagine if there is no Earth's magnetic field. Means imagine we don't know the magnetism comes from there. We don't know. Okay, so let us take Earth is not with the magnetic field. Then magnetic needle in the compass, can it deflect? No, because this needle deflects only because of the Earth's magnetic field. So that's what is the next point. Second point is, if we see that there is no Earth's magnetic field. If there is no Earth's magnetic field, so there will be no deflection. So the magnetic needle cannot be deflected. So we can conclude that Earth is itself producing magnetic field. See, if you move with the compass, holding the compass, and if you move anywhere on the Earth, that may be Hyderabad, that may be a Delhi, that may be Kashmir, whatever, or wherever the area is, always the compass shows the north direction. So here, this deflection happens anywhere on the Earth, then we can say Earth is only behaves as a magnet and itself is producing the magnetic field. So the magnetic field, see if you observe, see the next point is the magnetic field is decreasing. The magnetic field is decreasing if we move above the surface of the Earth. Above the surface of the Earth. Means if you move above the surface of the Earth, the magnetic field decreases. So the source of the magnetic field is the Earth. So finally, by doing all these discussions, what is that? With the help of tool, that is compass. Holding the compass, if you roam, means if you go around, the earth always shows the north direction of the earth. And if you move above the surface of the earth, the intensity of the magnetic field decreases. So with the help of these 2 points, then we can conclude that Earth itself is producing magnetic field. So finally, what is that? Finally, the Earth behaves like a magnet. And our scientists measure this magnetic field of the Earth is 10 power minus 5 Tesla. So we measure the magnetic field of the Earth is 10 power minus 5 Tesla. Okay, so with this we concluded, means we confirmed that the Earth has a magnetic field, and also we measure the value 10 power minus 5 Tesla. And with the help of same compass, we can do a few more points. That here, with the help of the magnetic compass, if we move along the north direction on the surface of the Earth, I'm repeating, holding the compass in your palm, okay, and moving. See, compass means what? It always shows the north direction of the Earth. Now, if you walk, if you move, if you keep on walking with the help of that tool, that is compass, the needle shows always north direction, and if you move along that direction, and it stops at the north direction of the Earth only. So here is the point, with the help of magnetic compass, if we move along the north direction on the surface of the Earth, that may be any situation, that raining, hot, day, night, whatever the situation is, it always shows the north direction of the Earth. Now the point is, what is meant by north direction of the Earth? This point is very important. Okay, so I am giving very deep information, try to understand. So here, what is meant by north direction of the Earth? Here, look at this picture here. Okay, so here is the yellow one is sun rays which are incidentally on the Earth here. Okay, so incidentally on the Earth here. Now, so where the light rays are incidenting, so that area is a day, and the other side is a night. And we know the Earth spins. We know the Earth spins, right? So spinning, due to spinning, so there you can see that the rotational axis. You can see the rotational axis. Okay, so this point is axis of the globe or the Earth. And if you observe, the whole body is moving, but near the axis point, that area will not be rotated. That area will not be rotated. That point will be fixed, and the remaining whole body is rotates. But along the axis point, this point will not be rotated. Okay, so here wherever the sun rays are incidenting, so that side, that direction, we treat this as an east direction. And exactly opposite to that, it is in west direction, and where the rotational axis is present and the point where it is not rotating, and that top point is called as a north pole. I'm repeating, in which direction the sun rays are incidenting, so that area, that direction, we treat that as an east, and opposite to that is in a west, and the axis point where the point is not rotating at the top of the globe or top of the Earth is a north pole, and exactly opposite to that means at a bottom, that is a south pole. So what is the answer here? What is meant by north direction of the Earth? Yeah, from the diagram, the points which are not rotating along the axis are called north pole and south pole of the Earth. Okay, so what is the north pole? That is at the point where the point is not rotating, means the remaining part of the Earth is rotating, but at the axis point it is not rotating. This is called north pole. And this information was explained by the study of geography. Okay, so this information is obtained from the geography. Okay, study of geography only. Okay, now at exactly north pole, the magnetic needle shows vertical direction, indicating the north pole of the magnet. Here, this point, this vertical direction, I will explain. Okay, so at exactly north pole, the magnetic needle shows vertical direction indicating the north pole of the earth. So for example, here is a needle, for example. Here is a needle. So if you hold this needle, see this colored one is a needle. It is, if you hold like this, it will show what is that, horizontal deflection. It will move the horizontal deflection. It gives only the horizontal deflection. Now, if you hold like this, then it will give vertical direction. Vertical. It is moving in vertical direction. Understood? See, if you hold like this, it is moving only the horizontal direction. And if it is hold like this, then it is moving vertical direction. Okay? It is y-axis and this is x-axis. This x-axis. Okay? X-axis and y-axis. Okay? So now if you are holding this compass needle and it is showing the direction west, then you are moving, north. Now you are moving this. You are walking along with this needle and you keep on walking and reaching at a particular point on the earth. There, north pole is ends. So exactly you are standing at the north pole. There, this magnetic needle shows the deflection downward. It's vertical. Understood? So, as long as you are walking on the earth, it shows the north direction, and the moment you reach the north pole, you are standing exactly at the north pole, and this needle shows this kind of deflection. This is called vertical direction. So, the last point is, at exactly north pole, the magnetic needle shows vertical direction, indicating that is a north pole of the earth. Okay, now here look at this. We suppose that the north pole shown by the magnetic needle is not the geometrical north pole. I'm repeating. The north pole shown by the magnetic needle. See, you hold the magnetic compass and it's showing that it is the north pole. But geometrical north pole is different. What is geometrical north pole? Means physically, this globe in a sphere shape that has a center point. Look at this diagram, is indicated with a green point. Okay, so this green dot indicates geometrically it is the center point, it's the top edge. That is, north pole is structurally, geometrically. It is giving the point is a geometrical north pole. Now, but our needle, it is not showing this point, it is showing another point, it is colored with a red, you can see it is a red dot, is indicated by the magnetic needle. And the needle shows this point as a north pole, and but geometrically this green point shows that this is a north pole. So here is some differences comes here, and I'll explain in the next point that why it is happening. Okay, why it is happened we'll discuss now. So here the green dot is what is it? Structurally, geometrically is the center point, and this red dot is the north pole indicated by our tool, that is magnetic compass needle. Okay, so that's why we surprised that north pole shown by the magnetic needle is not the geometrical north pole. Why this happens, we'll discuss. Now, the north pole is indicated by the magnetic needle is called magnetic north pole. See, observe the means here, observe the terms here. North pole is indicated by magnetic needle. Okay, north pole is indicated by the magnetic needle is called magnetic north pole. Observe the terms, magnetic north pole. And if the same north pole is indicated by the geometrical point, means geometrical center. Okay, I'm repeating, magnetic needle. Due to the magnetic needle, then that point is called magnetic north pole, and due to the geometry, and this north pole is called geometrical north pole. So we have two north poles here. One is due to geometrically centered, that is geometrical north pole, and another point is due to our magnetic needle. So we have two north poles here, that is one is due to geometrically centered one and another one is due to our magnetic needle. See, observe the terms, that is magnetic north pole and geometrical north pole. Okay, one is magnetic north pole and another one is geometrical north pole. So hence the magnetic north pole and geometrical north poles are not same. So this point is to be understood. Okay, now moving to deep into this concept. Okay, just you understood what is the north pole and what type of north poles are present. What is north pole? That is the point where it is not rotating, even the whole globe is rotating, whole earth is rotating, but at the axis rotation, there the point is not rotating, so that is called the north pole. But that the north poles are two types, that is one is geometrically centered, one is a geometrical north pole, and another north pole is indicated or shown by the magnetic needle, that is magnetic north pole. So hence both magnetic north pole and geometrical north poles are not same. So now the line joining the magnetic north pole, observe this terms. The line joining the magnetic north pole and the magnetic south pole is called magnetic axis. So here magnetic north pole is there. Similarly, the other side of the globe, other side of the earth, definitely there will be magnetic south pole. Yes, so the line joining through the earth from the top of the globe to the bottom of the globe, if you draw a line or a line passing through the magnetic north pole to the magnetic south pole is called magnetic axis. Magnetic axis. And similarly, the line joining from the geometrical north pole to the geometrical south pole. Okay, so here we are passing two lines. One is from magnetic north to the magnetic south. Another one is geometric north to the geometric south. So the line which is passing from magnetic north to the magnetic south pole is called magnetic axis, and the line which is moving from geometrical north to the geometrical south is called geometrical axis. So try to understand the terms here. Okay, so here is the diagram, clear picture here. Look at this. Observe the diagram first. Right? So here is indicated with the north. This is structurally or geometrically. This is north pole. Okay, this is north pole is given by the information geography. Exactly opposite to this, south pole is there. Okay, exactly opposite to this, south pole. So the line which is passing from north to the south is called geometric axis. And exactly, see, at some other distance, one more point is identified as a magnetic north pole. Have you observed? Magnetic north pole. And exactly opposite to this is a magnetic south pole. Okay, magnetic south pole. Right, so a line which is passing through this is called magnetic axis, and the angle between these means the difference between these geometrical pole, the geometrical axis and the magnetic axis is approximately 11.3 to 11.5. That value changes from position to position. So here the difference between the magnetic axis and the geometrical axis is 11.3 as per your textbook. Okay, now the location of north magnetic pole is, have you observed this diagram here? Okay, as per our textbook, that north means NG is a geographical north, and N is given, that is magnetic north. Okay, this is geometrical north and this is magnetic north. And similarly here, opposite to this is a magnetic south and it is a geometric south. And equator is also changed with respect to their poles. Okay, there is this is called magnetic equator and this is called geometrical equator. So here locations, if you observe, the location of a north magnetic pole is, see these values that we can get it from the Google Maps. You can get it the Google Maps exactly. Okay, this location means where this north magnetic pole is present at this altitude and latitude here, 79.74 degrees north and 71.8 degrees west. Okay, right? So similarly, exactly opposite to that is a south pole. So location of the south magnetic pole. South magnetic pole here it is. So this is opposite to this position is 79.74 degrees, but it is 108.22 degrees. See this from the geometrical equator, this position of this south magnet, okay, magnetic south is displaced at this angle, that is 108.22 degree towards east. Okay, so see, if you observe there on the earth, if you see at these altitudes and all, the area is north and on the top, and at the bottom, the south, magnetic south is located in the Antarctica. Okay, so these places are exactly magnetic south and magnetic north are present. Okay, and here. So with the above discussion, we proved that the existence of Earth's magnetic field and its direction. See, actually, what is our title? Earth as a magnet. Earth as a magnet. So we have proved that with so far discussed that Earth has some magnetic field. Now the condition is what causes producing the magnetic field. Means just like that, the Earth how it is behaves like a magnet. So with the above discussion, we proved that the existence of Earth's magnetic field and its direction. So we identify directions also, north and south directions. Now the point is, what is the cause of producing the magnetic field by the Earth? What is the cause of producing the magnetic field by the Earth? So initially, so there were so many theories, okay, and still one theory we are accepting. That is also the works are going on that. So initially there was a thought that the Earth is full of iron and cobalt. I'm repeating. Initially there was a thought that the Earth is full of iron and cobalt metals, which are present exactly at the core of the Earth and which is producing the magnetic field. That is producing the magnetic field. Because of this iron and cobalt, which is present hugely at the center of the core of the Earth, and we are thinking, we have thought that because of that, Earth is behaving like a magnet. But later on, originally we know that at the center of, at the core of the Earth, there is a huge temperature present, that everyone knows that at the center of the Earth, there is a huge temperature. So because of that temperature, this means the question is, magnetism cannot be exist at a high temperature. That point needs to be understood. Okay, that point needs to be remembered that at high temperatures, it loses its magnetism. So here at high temperatures, there will be no existence of magnetic field. So keeping this point, there was another the theory is involved. Means involved that later on the molten metal produces the ions. Okay, so initially what was the thought? The huge metals are present at the center, but we know that at the center there will be a high temperature, and because of the high temperature we know that there is no existence of the magnetic field. But later on what happened? The iron, which is metal, will be not in the solid state, it is in a liquid state, that is a molten state. So later on, the molten metals are producing. So due to this, at this state, it produces, the molten metal produces some ions, releases some ions. And these ions are having some charges. And these charges are rotating, because we know that the Earth is rotating. Earth is in a spin motion, rotating. So whenever these charges are moving, that everyone knows that whenever the charge is moving per unit time, that it produces current. Okay, the charge is moving per unit time, produces current. So here the ions are produced due to the molten metal, and those are under motion, and means those are the charge and they are moving, means under motion, then produces current. And whenever there is a current and perpendicular to that, the magnetic field is generated. So it means always both magnetic field and the electric field are perpendicular to each other. So due to this ions which has charge and they are moving and it produces current and perpendicular to that magnetic field will be generated. So this is the present the theory that we are accepting nowadays. Okay, so now there is one more contradiction here as per our previous discussion that the compass is moving, compass that we are taking. See, first try to understand what is the function of compass here. So I told you it is a 5D shaped magnet. Okay, so that always shows the north direction, shows the north direction. Okay, north direction of what? North direction of Earth. So we know here like poles repel, like poles repel, unlike pole attracts. But our magnetic needle, that is north pole of the magnetic needle and north pole of the Earth, both are attracting each other. Both are attracting each other. Okay, so how it is possible? This is what is the contradiction here. Okay, magnetic compass needle shows the north direction and north direction of the Earth. Both are attracting. How it is possible? This is what is the contradiction. So another imaginary concept that there is a big magnet inside the Earth and that shows south pole upwards as shown in the figure. Yeah, look at this diagram here. Look at this. Here, this is what's it? Earth here. Observe the 2 points here. Geometrically centered one is a north pole, and observe this huge magnet. I told you why geometrical north pole and magnetic north pole are separated. It's not exactly the center. So this could be the reason that here the center point is the geometrical center. Okay, and another point is just far away from the geometrical point is made with the what's that north magnetic pole. So with this, what to conclude? See, the freely suspended magnetic needle, that is north direction of this magnet is indicated, is attracting towards this south. Okay, so this is only the possible. What is the possibility? North always attracts towards the south. So what is that imaginary concept that inside the Earth there is a huge magnet that is upward, upside is a south pole and downward is a north pole. Okay, so that's why if we are standing exactly at the this north pole, north magnetic pole with the compass, and I told you in the beginning that compass needle shows vertically downward, means it is strongly attracting at that point with the south pole. That needle attracts exactly with the south pole of the magnet, that is this Earth. So with this, what we can conclude that at the surface, and on the surface of the Earth, it is showing north pole, but inside this Earth, we are thinking that it is an imaginary concept that there is a big magnet inside and shows south pole upwards. So that's why our magnetic needle is attracting towards this. So on the surface, it is just a north pole. Okay, so this is the concept. And characteristics of Earth. So to make this our discussion to be very strong, that we need to discuss a few more concepts, that is characteristics of Earth's magnetic field. The whole discussion of this thing is segregated into the 3 important concepts, that is magnetic declination, magnetic inclination, and horizontal component of Earth's magnetic field. So here, magnetic declination is indicated with the theta here. So these 3 give the complete information on the Earth's magnetism. Now, in the very beginning that we discussed that magnetic axis and geometrical axis and magnetic axis. That is, if we made a cut like this, the Earth cut into like this, then this surface area, this surface is called meridian. See, look at this. A line on the Earth's surface, approximately a greater circular path passing through north and south poles is called meridian. See, the terms that you should understand properly. Meridian. Okay. this is what total surface area from north to south. If we made cut the earth looks like this, and this surface area that is called, this area is called is a meridian. Okay. So now we will elaborate with this. See, we are going to discuss now the 3 points, that is magnetic inclination or tip, and horizontal component of Earth's magnetic field. So here, if we made cut the Earth from the magnetic north pole to the magnetic south pole, here look at this diagram. We have 2 north poles here. One is geometrical north pole and another one is magnetic north pole. So here we are making a cut from the magnetic north pole to the magnetic south pole, then that plane surface is called magnetic meridian. Magnetic meridian, very important. Magnetic meridian means what? First of all, you should understand what is north pole. And north poles we have 2 types. One is geometrical north pole, second one is a magnetic north pole. Now you need to understand what is meridian and magnetic meridian. What is magnetic meridian? Now, if you cut the Earth from the magnetic north pole to the magnetic south pole, then that plane surface area is called magnetic meridian. Similarly, if you cut from the geometrical north pole to geometrical south pole, then that plane circular surface is called geometrical meridian. See, observe this. So, if you cut from the geometrical north to the geometrical south, and that is called geometrical meridian. And if you cut from the magnetic north to the magnetic south, then that is called magnetic meridian. Okay, right? And see, the angle between the magnetic meridian and geometrical meridian at a particular point means this position is very important. Means where these 2 planes that you are observing is very important. Yeah, look at this diagram. See here, red dot is there. So red dot is a geographical north pole, and here the green dot is a magnetic north pole. Okay. So if you observe from different points, here is given magnets, black and white is the magnets here. So if you observe this magnetic north pole, all the magnetic north poles are attracting towards the magnetic north only. They are not attracting towards the geometrical north. They are pointing towards the green color. See, all are pointing towards the green. Have you observed? So this is what the magnetic north. But geometrical north is here, red white. Okay, now the angle between these 2 is indicated with the D here. Look at this. It's a plus D and minus D. So this angle is called angle of declination. This angle is called angle of declination. Okay? Understood? So the compass needle points to the magnetic north. See, all the compass needles are pointing to this point, and originally this is what geometrical north pole, and the angle between this position is very important, that from where you are looking. See, for example, I kept like this. Okay, this is, for example, geometrical north, and this is, for example, is a magnetic north. Okay, from my side or from your side, we are looking these 2 is separated from distance. So from your side or from my side, is these 2 are separated, and these 2 are making some angulars. But the person who is standing here, means the person who is standing here looking these 2 points, magnetic point and geometrical point. For this person, these 2 appears at the same line. Means these 2 are not making any angle. Both are same line. So for example, I kept like this. So for you or for me, and both this end and this end, means both the edges appears like a straight line. Means both are at the same line. So there is no difference, there is no angle. So this angle depends on the position from where you are looking. So that's why the people who are standing living in Delhi, the people are living in Kanyakumari, and for the people who are living in Sikkim, Agartala means that side, and the people are living in Gujarat and that side, for all of them, the 4 corners of the country, where different angles can be observed. This is angle of declination. The position to position is changes. So the angle is not same at all the points on the earth, and the values of this declination changes from place to place. Okay, so here is another point is the angle between the intensity of Earth's magnetic field. See, this is very important. This comes to inclination. This is inclination. Right. So the angle between the intensity of Earth's magnetic field and the horizon, that is surface of the Earth. See here, up to now, you might have an idea that always the magnetic needle shows not the direction. Means it is only moving like this, only on the horizontal. If you hold this magnetic compass, it is always shows the horizontal deflection only. If you hold like this, it shows vertical deflection. So this is the Earth surface and intensity. I told you that if you are exactly standing at the North Pole, this this compass shows this deflection. Means exactly vertical, exactly vertical. Okay, if you are keeping, see if you are coming from somewhere and reaching to, if you are coming from somewhere, this needle shows like this. Okay, exactly you are reaching at the top point, that is north pole of the magnet, then north pole of the water, earth, then this needle shows like this, like this. Okay, so at normal places it is always north and south direction, and exactly you are reaching at the pole of the earth, then it indicates this direction. So in what direction you hold it? If you hold it like this will show like this, means vertical. If you hold it like this, it will show like this. This is horizontal. Now you observe the diagrams here. This diagram is showing only horizontal, and this direction is showing. Look at this. Is a vertical direction. Okay, so this dotted line is a surface of the earth, and this magnetic needle direction is what we said. What that inclined like this. So because there the strong magnetic field is there, wherever the strong magnetic field is there, it will incline, tilt there. If there is a feeble amount of magnetic field is there, it will free to rotate. But whereas the strong magnetic field is there, it will strictly attract towards the magnet. That's what is happening. So the angle between the surface to the angle of tilting, at what angle this vertical deflection is made. So this is called magnetic inclination or dip. So the magnetic needle is allowed to move in a vertical direction, then it shows the intensity of Earth's magnetic field. So where this magnetic needle shows more deflection, then that is angle of deflection. Okay, so we'll stop here. We'll continue in the next class. Okay, we'll continue next class as time's up. Thank you.
Start, sir.